Hi, my name is Mama Aizin Berusni and my metric number is A20MJ0044. Today I will be explain atmospheric dispersion modeling. So, what is atmospheric dispersion modeling? Atmospheric dispersion modeling is the mathematical simulation of how air pollutants disperse in the ambient atmosphere. To solve the mathematical equations and is used to estimate the downwind ambient concentration of air pollutants, vehicular traffic or accidental chemical release, and predict future concentration under specific scenarios such as changes in emission sources. Next is dispersion in physical context by influenced by various factors such as emission sources, various sources such as industrial facilities, vehicles, power plants and other combustion process. Second, in topography, impact on the dispersion of pollutants such as valleys and urban canyon, buildings, hills and other obstacles affect the flow and dispersion patterns of pollutants. Third is chemical reaction and transformation. Undergo chemical reaction or transformation in the atmosphere, affect their composition, behavior, and the spatial distribution of their byproduct. And the last is initial mixing. Initial plump of pollutants may exhibit characteristics such as buoyancy and turbulence, affecting its vertical and horizontal dispersion. Alright, this is the first equation in dispersion. Atmospheric dispersion model, which is the Gaussian model. This model assumes that the pollutant disperse in Gaussian shape, forming a bell-shaped curve. It is simple to use and widely applied in dispersion modeling. So this is a double Gaussian model equation shown that will equal C is a steady state concentration at a point, and this is the model for Gaussian model. This slide shows atmospheric stability estimation, where for the first figure is mathematical dispersion of pollutant underground, while for the second figure is the reflection of the mathematical dispersion of pollutant underground at the first figure. Alright, for second equation, atmospheric stability classes, where a method used to categorize an atmosphere based on its tendency for a parcel to move upward or downward after being displaced vertically. This classification is essential for understanding air dispersion, air quality, and the potential for air pollution. For the first figure is table of stability classification, where the information given is first, surface wind speed is measured at 10 meters above the ground. Second, correspond to clear summer day with sun higher than 60 above the horizon. C corresponds to a summer day with a few broken clouds or a clear day with sun 35 to 60 above the horizon. For D, horizon to a fall afternoon or cloudy summer day or clear summer day with the sun's 15 to 35. For E, cloudiness is defined as the fraction of sky covered by clouds. And for F, for AB, BC or CD condition, average the values obtained for each, where A equal to very unstable, B equal to moderately unstable, C slightly unstable, D equal to neutral, E slightly stable, and F stable. Regardless of wind speed, class D should be assumed for overcast condition day or night. And the second table is the numerical values for constant equation and are given in 20.2. The following example illustrate typical use for the information presented in the past few pages. So this is table of values of curve fit constant for calculating dispersion coefficient as a function of downwind distance and atmospheric stability, using stability A, B, C, D, F, C until F, and the capital of A, B, C, D, E, F following the given information in the first table. Alright, for the third equation is the dependence of concentration on averaging time, while the dependence of concentration on averaging time refers to how the time average concentration of substance, such as a pollutant, varies with the duration of the averaging interval. So this is the equation for concentration at 2 averaging time. For the fourth is estimating the maximum downwind ground level of concentration. The maximum downwind warm level concentration always occurs on the satellite. Turner 1917 developed a graphical means of estimating the maximum concentration Cmax and the distance at which it occurs for Xmax. Both Cmax and Xmax depend on stability class, effective stack height, wind speed, and emission rate. So the equation shown is polynomial equation with following table of values of curve fit constant of estimating from H as a function of atmospheric stability. So this is fifth equation, which is estimating the downwind concentration under an elevated inversion, which have two equations, which are Trapped-Plum equation and concentration outlet equation that's shown in this slide. Okay, for this slide is to explain tall stack and plumb rise include buoyancy effects. For taller stacks disperse pollutants more effectively than shorter stacks because the plumb has to travel through a greater depth of the atmosphere before reaching the ground level. As the plumb travels, it spreads and disperses and pollutant degradation increases. So the following table is height of tall things. Such as stacks, the type of stacks and buildings, and their feet given. And plumb rise refers to the vertical displacement of the air pollutant plumb due to buoyancy effects. The rise of the plumb can be influenced by various factors such as the stack height, atmospheric stability, and moisture content. And this is the following gives a plumb rise equation. For the buoyancy effects can cause the plumb to rise, leading to better dispersion of pollutants. The plumb rise can be estimated using the effective stack height, which is the actual height from which the air pollutant is released into the atmosphere. And this is the following given is a buoyancy equation. Alright, this is one of the example which of critical wind speed. Which is consider the following data: Q equal to 110 gram per second for class D with height 100 meter, MW which is 28.9, PA equal to 100 MB, and QH equal to 10 MW. Using the Briggs-Plumb rise equation, calculate Cmax as a function of wind speed and find the critical wind speed, the maximum Cmax, and the distance at which it occurs. And the following, this is equation we will be used. And the solution is given in the table. The critical wind speed at stack height for class D, stability lies between 8.3 and 9.7 meter per second, and result in Cmax is of 32 microgram per m cube at distance between 6 and 6.5 kilometer. As shown, as shown the answer, I highlight that. Alright, for the subject, the other stack design consideration have two examples, which is typical flow disturbance owing to a building, and second is typical flow disturbances owing to a stack. Following the example, which is a source emits 20 grams per second of pollutant content in 6,000 meter cube per minute of stack gases at pressure equal to 1 atm and temperature is 390 Kelvin. The maximum expected sustained wind speed at stack height is 15 meter per second. The heat emission rate is 7 MW. For a wind speed of 8 meter per second at all heights and class D stability, design a stack, specify the height and diameter that will prevent ground level concentration from exceeding 50 microgram per meter cube anyway downwind. Use the Holland formula for plumb rise. For the solution, the inner stack diameter is calculated first. The stack gas velocity is set by Vs equal to 1.5 times to 15 meter per second equal to 22.5 meter per second. From the Vs we obtain, the stack diameter will be calculated by the continuity equation. From the Q equation, we can formulate to find the ds. So the ds equal to 4q over pi times to Vs to the power of half equal to 2.5 meter. For the condition of this problem, we will be use a polynomial equation from the slide before and insert the information to get 2.0 times 10 to the power of negative 5 meter to the power of negative 2. From the figure 2.9 or table at the intersection of this value of Cu over Q max and the class D stability line, we will get the values of H and X max are found in the given below, which is H equal to 68 meter and X max equal to 1.7 kilometer. From the Holland formula, we have delta H equal to 1.5 times to 22.5 and 2.4 that we get from the equation above over 8 plus 9.6 over 8 times to 7 equal to 18.5 meter. Thus, little h will be get from h minus delta h equal to 49.5 meter. Specify a stack 50 meter tall and with a top in a diameter of 2.4 meter. Alright, for computer program for dispersion modeling, there are three modeling, which is IM-Tech Dispersion, a software program that models chemical gas releases and enable users to visualize the most credible industrial scenarios. For the second is Mohd, an advanced air dispersion model that calculates the concentration of pollutants emitted from point, line, and area sources. It includes algorithms that take into account the effects of complex terrain, plumb rise, and chemical reaction. And the last is ADMS, the Atmospheric Dispersion Modeling System, is an advanced dispersion model that calculates the concentration of pollutants emitted from point, line volume, and area sources. Alright, for subchapter mobile sources and line sources model, the figure shown is the finite length line source FLLS model. Description where a uniform average emission rate Q is defined for the FLLS in units of microgram per meter second. The x-axis is parallel with the wind and passes through the receptor. The y-axis is collinear with the FLLS, which is perpendicular with the y direction. Since sigma y and sigma z are constant with the respect to y, this equation, above equation, can be integrated over the FLLS and written as follow the equation below that. C equal to K per 2 pi sigma y integrate y1 to y2 exponent to negative y squared over 2 sigma squared y dy, where K the reason of leaving the quantity 2 pi sigma y out of the constant K will become obviously shortly. Alright, for the conclusion in this chapter, atmospheric dispersion model will become predictive tool, which is essential tool used to estimate the spatial and temporal distribution of air pollutants emitted from industrial sources, transportation, and other human activities. Second, factors considered, which is these models take into account a range of factors including meteorological condition such as wind speed, direction, and stability, source characteristic, pollutant properties, and topographical features to stimulate the complex processes involved in dispersion. And the last is atmospheric dispersion model will be an emergency response, such as for like in the event of accidental releases or industrial incidents. Dispersion model can be valuable for emergency response planning. So that's all for the explanation of atmospheric dispersion modeling. Thank you.